Hey guys, welcome to another episode of the Human AI podcast. Today we're going to talk about blood volume and red blood cells. It's going to be a short podcast than the usual ones. If you're unfamiliar with the structure of the podcast, Grok and AI and I talk about topics that I'm quite unfamiliar with. Grok explains some things to me, and I then learn more things about that topic. Take everything that AI says with a pinch of salt. Cross-reference everything you hear. However, I do hope you find this information valuable and you find the podcast enjoyable. Let's start, Grok, with blood volume, perhaps diving into its regulation by the kidney too.
All right, let's dive into blood volume and how the kidneys regulate it. Blood volume is the total amount of blood in your body, typically around 5 liters in an average adult. It's made up of plasma, which is the liquid part, and red blood cells, which carry oxygen. Maintaining the right blood volume is crucial for blood pressure and overall circulation. The kidneys play a big role in regulating this. They filter blood and adjust how much water and sodium get reabsorbed or excreted. If blood volume is low, like from dehydration, the kidneys release an enzyme called renin. This kicks off a chain reaction producing angiotensin II, which tightens blood vessels and signals the release of aldosterone. Aldosterone tells the kidneys to hold on to more water and sodium, increasing plasma volume and, in turn, blood volume. On the flip side, if blood volume is too high, the kidneys can excrete more water and sodium to bring it down. They also respond to hormones like antidiuretic hormone, or ADH, which fine-tunes water retention. It's a tight system to keep everything balanced. Want me to zoom in on red blood cells next, or stick with the kidney's role?
I want to ask you about circulatory capacity. What's that? So, we sum the inside volumes of every blood vessel in the body, and then anything empty is that capacity, or no? Yeah. All right. So if the pressure increase, so vasoconstriction means smaller capacity.
Okay, let's clarify circulatory capacity. It refers to the total volume that the circulatory system, meaning all the blood vessels like arteries, veins, and capillaries, can hold at any given time. Think of it as the maximum space available for blood within the system. It's not about empty space. It's the collective volume of all those vessels, whether they're filled with blood or not. In an average adult, this is roughly 5 to 6 liters, matching the typical blood volume, since the system is designed to hold that amount under normal conditions. Now, you mentioned vasoconstriction and pressure. Vasoconstriction, when blood vessels narrow, doesn't exactly reduce the total circulatory capacity in a structural sense. It reduces the effective diameter of the vessels, which increases blood pressure because the same amount of blood is being pushed through a smaller space. The overall capacity of the system stays the same, it's just that the blood is more tightly squeezed. Conversely, vasodilation, where vessels widen, can lower pressure by giving blood more room to flow. Does that clear it up? Want to tie this back to blood volume or move to something like how red blood cells fit into this?
Well, I'm just a bit confused, dude, because of what circulatory capacity, excuse me guys, is, because you're saying it's everything inside the vessel, the empty space, and the fluid, basically.
No worries. Let's straighten this out. Circulatory capacity is essentially the total volume inside all your blood vessels, arteries, veins, capillaries, the whole network, if they were filled to their normal extent. It's not about empty space sitting there. It's the maximum amount of blood the system can hold, which matches your blood volume, around 5 liters in an average adult. The vessels are designed to contain this volume of fluid, blood, which includes plasma and red blood cells, under normal conditions. So, it's not empty space plus fluid, it's just the space that holds the blood. When I mentioned vasoconstriction earlier, it might have sounded confusing. It doesn't change the total capacity of the system, It just squeezes the vessels, increasing pressure by reducing the space blood flows through temporarily. Clearer now?
No, it's
Want to?
not clearer now.
All right, let's break it down simpler. Circulatory capacity is just the total space inside all your blood vessels combined, like the full container size of your circulatory system. In a typical adult, this space holds about 5 liters of blood, which is your blood volume, made up of plasma and red blood cells. There's no empty space in this equation. The vessels are normally full of blood. It's like saying a 5-liter jug is the capacity, and it's filled with 5 liters of liquid. No extra room, no gaps. When vessels constrict or dilate, they change how tightly the blood is packed in, affecting pressure, but the overall container size of the system stays the same. Does that help, or should I try another angle?
So the capacity doesn't change with vasoconstriction.
Exactly. Vasoconstriction doesn't change the total circulatory capacity. The capacity is the fixed volume of all your blood vessels combined, like the total size of the container that holds your blood, roughly 5 liters in an adult. Vasoconstriction just narrows some of those vessels, squeezing the blood into a tighter space, which raises blood pressure. The overall volume the system can hold stays the same. It's just redistributed or pressurized differently. Make sense now? Want to connect this to something like plasma volume or keep going with this?
I see. Okay. Let me ask you about blood pressure now. So, blood volume increases blood pressure, vasoconstriction increases blood pressure, and high cardiac output increases blood pressure. Explain this a bit to us.
All right, let's unpack how blood volume, vasoconstriction, and cardiac output affect blood pressure. Blood pressure is the force of blood pushing against artery walls, driven by a few key factors. First, blood volume. If your blood volume goes up, like from retaining more fluid, there's more blood pushing through the vessels, which increases pressure. Think of overfilling a water balloon. It gets tighter. Second, vasoconstriction. When blood vessels narrow, the same amount of blood flows through a smaller space, ramping up pressure, like squeezing a hose. Third, cardiac output. This is the amount of blood your heart pumps per minute. If your heart pumps harder or faster, say during exercise, it pushes more blood into the system, raising pressure. These three work together. For example, if blood volume is high and vessels are constricted, pressure spikes even more because the heart's pumping against a tighter, full...
Got it. Just a reminder, Grog. Answer with the least amount of words while also getting your point across. Well, we've talked a lot, guys, in the previous episodes about the kidney and filtration and the glomerulus. Grog, give us a couple of sentences regarding that. And then I want to ask you about vasoconstriction and vasodilation of the afferent and efferent arteriole and how they change things.
The kidneys filter blood in the glomerulus, removing waste and balancing fluids. Afferent and efferent arterioles control blood flow to the glomerulus. Vasoconstriction of the afferent arteriole reduces blood flow, lowering glomerular filtration rate. Vasodilation of the afferent increases flow, raising filtration. Efferent arteriole vasoconstriction raises glomerular pressure, increasing filtration. Efferent vasodilation lowers pressure, reducing filtration. This balance regulates how much fluid and waste the kidneys process. Want more on this?
That's good. And what about blood urea nitrogen? Tell us about that.
Blood urea nitrogen, or BUN, measures the amount of urea nitrogen in your blood. Urea is a waste product from protein breakdown, filtered by the kidneys. Normal BUN levels are about 7 to 20 milligrams per deciliter. High BUN can signal kidney issues, dehydration, or high protein intake. Low BUN might mean liver problems or malnutrition. It's a key marker for kidney function and overall metabolism. Want to tie this to glomerular filtration or something else?
I want to ask you a bit, and we've talked about it in the previous episodes, serum creatinine and how it's involved. And then we'll go to ADH.
Serum creatinine is a waste product from muscle activity, filtered by the kidneys. Normal levels are about 0.6 to 1.2 milligrams per deciliter. High levels suggest kidney dysfunction, as the glomerulus isn't filtering it well. It's a key marker, alongside BUN, for kidney health. Antidiuretic hormone, or ADH, controls water reabsorption in the kidneys. When blood volume or pressure is low, ADH is released, making kidneys reabsorb more water, concentrating urine and raising blood volume. Too much ADH can lead to water retention, too little to excessive urination. Want to dive deeper into ADH's role or loop back?
No, this is great. Why don't we talk a bit about where ADH is secreted from? Well, specifically posterior pituitary, but I just want to understand why that's the ideal place for it to be secreted from. And let's talk a bit about diuresis, loss of plasma fluid into urine, and perhaps you could explain that and when it increases and decreases too.
ADH, or antidiuretic hormone, is secreted by the posterior pituitary gland, which acts as a release site for hormones made in the hypothalamus. The hypothalamus senses low blood volume, high blood osmolar aridity, or low blood pressure, triggering ADH release to conserve water. Diuresis is the increased production of urine, leading to loss of plasma fluid. It increases when ADH levels are low, like in diabetes insipidus, causing excessive water loss and dilute urine. It also rises with diuretics, or high fluid intake. Diuresis decreases when ADH is high, as water is reabsorbed, concentrating urine and preserving plasma volume. This balance keeps blood pressure and hydration stable. Want to explore more on this or something else?
Interesting. Why don't we talk a bit about mineral corticoids? So aldosterone is called a mineral corticoid and it's secreted from the adrenal cortex. Explain to us why it's called like that and why from the adrenal cortex. Yeah. Tell us what it does in regard to sodium too. And
Aldosterone, a mineral alkaloid, is named for its role in regulating minerals, especially sodium and potassium. It's produced in the adrenal cortex, the outer layer of the adrenal glands, because that's where steroid hormones are synthesized from cholesterol. Aldosterone acts on the kidneys, promoting sodium reabsorption in the distal tubules and collecting ducts. This increases water retention, raising blood volume and pressure. It also boosts potassium excretion. The renin-angiotensin system triggers its release when blood volume or sodium levels drop. This helps maintain electrolyte balance and blood pressure. Want to connect this to something else?
what is mineral, the translation in Greek?
The word mineral in Greek is orikto. Orikto. Want me to
or metallevma. Okay. Anyway, okay, let's talk a bit about, well, we can't avoid mentioning angiotensin too, but I am a bit confused. I'm not going to lie about the previous two questions I asked you. I didn't really understand your answers. Perhaps if you could simply explain the answer and also touch on the RAAS. So explain the last two answers, specifically what I asked you, nice and simply, in a couple of sentences, and then talk to us a bit about the RAAS too.
All right, let's simplify. ADH comes from the posterior pituitary because the hypothalamus makes it and sends it there for release. It helps kidneys reabsorb water when blood volume or pressure is low. Diuresis is when you lose more plasma fluid as urine, increasing with low ADH or diuretics, and decreasing when ADH conserves water. Aldosterone, a mineral alkaloid, is called that because it controls minerals like sodium. It's made in the adrenal cortex, and makes kidneys reabsorb sodium to boost blood volume. Now, the RAS, renin-angiotensin-aldosterone system, kicks in when blood pressure or sodium drops. The kidneys release renin, which forms angiotensin II, tightening blood vessels and triggering aldosterone release. This raises blood volume and pressure by retaining sodium and water. Clearer now? Want to dive deeper?
It's clearer, but to be honest with you, I don't think it's a good answer to say, well, it's in the posterior pituitary because it's in the posterior pituitary. That's basically what you said. I'm asking why. I want to go a bit deeper into why it's the way it is, not that it's the way it is. Yeah, once we do that, I want us to touch on the B-type natriuretic peptide.
Fair point. Let's dig into why ADH comes from the posterior pituitary, and then hit B-type natriuretic peptide. The hypothalamus makes ADH, but it's stored and released by the posterior pituitary because it's an extension of the brain's neuroendocrine system, designed to quickly secrete hormones into the bloodstream. The hypothalamus senses signals like low blood volume or high osmolar aridity and sends ADH via nerve cells to the posterior pituitary for release, allowing rapid response to regulate water balance in the kidneys. This setup is efficient for fine-tuning blood volume and pressure. Now, B-type natriuretic peptide, or BNP, is a hormone released by the heart, specifically the ventricles, when they're stretched by high blood volume or pressure. It signals the kidneys to excrete more sodium and water, reducing blood volume and easing heart strain. It also relaxes blood vessels, lowering pressure. BNP acts as a counterbalance to RAS, preventing fluid overload. Want to circle back to anything or keep going?
So, explain to me the name B-type natriuretic peptide.
The name B-type natriuretic peptide breaks down like this. Natriuretic means it promotes sodium excretion in urine, which reduces blood volume. Peptide indicates it's a small protein. B-type distinguishes it from other natriuretic peptides, like A-type, and refers to its primary production in the brain initially, though it's mostly from the heart's ventriculus. So, BNP is a heart-released hormone that lowers blood volume and pressure by flushing out sodium and water. Clear enough? Or want more on its role?
So it reduces fluid overload. So it's the opposite of renin.
Yeah, exactly. BNP works against the renin-angiotensin-aldosterone system, while renin kicks off a process to increase blood volume and pressure by retaining sodium and water. BNP counters this by promoting sodium and water excretion, reducing fluid overload and easing pressure on the heart and vessels. It's like a brake pedal to renin's gas pedal. Want to dive deeper into how they balance each other?
Tell me about the erythropoietin EPO. So it's a cytokine / hormone. Why? I don't know. So explain to us. It drives erythropoiesis. And why is it made in the kidney? Yeah.
Erythropoietin, or EPO, is a hormone, sometimes called a cytokine, because it acts on cells that drives erythropoiesis, the production of red blood cells in bone marrow. It's made in the kidneys, specifically in specialized cells near the proximal tubules, because the kidneys monitor blood oxygen levels. When oxygen is low, like in anemia or high altitude, these cells sense it and release EPO to boost red blood cell production, improving oxygen delivery. The kidneys are ideal for this role since they filter blood and are sensitive to oxygen changes. Want more on EPO's effects or something else?
Well, so it creates blood cells.
Yeah, EPO stimulates the bone marrow to make more red blood cells, which carry oxygen around the body. It doesn't create them directly, but signals the marrow to ramp up production when oxygen levels are low, like in anemia or low oxygen conditions. Clearer now? Want to explore how this ties to kidney function or another angle?
Well, I would like to understand a bit. Okay. Osmotic and hydrostatic pressure. So, hydrostatic pressure out, osmotic pressure in. What's going on here? Why is it higher, the net pressure in the arterial end than in the venous end?
All right, let's unpack osmotic and hydrostatic pressure in the context of capillaries, since that's likely what you're referring to. Hydrostatic pressure is the force of blood pushing outward against capillary walls, driving fluid out into tissues. Osmotic pressure, mainly from proteins like albumin and blood, pulls fluid back into capillaries. At the arterial end of a capillary, hydrostatic pressure is higher, around 35 millimeters per hectoliter, because it's closer to the heart's pumping force, so more fluid gets pushed out. At the venous end, hydrostatic pressure drops to about 15 millimeters per hectoliter as blood flow slows, while osmotic pressure stays relatively constant, around 25 millimeters per hectoliter, pulling fluid back in. The net pressure is higher at the arterial end because the stronger hydrostatic push overcomes the osmotic pull, leading to fluid leaving the capillary. By the venous end, lower hydrostatic pressure lets osmotic pressure dominate, drawing fluid back. This balance keeps fluid moving between blood and tissues.
That makes sense. Let's talk a bit about congestion now. So, fluid goes into a vessel, but it can't leave, or maybe it's obstructed. So we have this build-up of pressure. And now, what? We have leakage. Tell us about this. Tell us about the damming or backwards theory.
Congestion in the circulatory system happens when blood flow backs up, often because of an obstruction or reduced outflow, leading to a buildup of pressure. Imagine a vessel where blood enters but can't exit easily, like a clogged pipe. This can occur in conditions like heart failure, where the heart can't pump blood out effectively, or in venous thrombosis, where a clot blocks a vein. The backup increases hydrostatic pressure in the vessels upstream, forcing fluid out of capillaries into tissues, causing leakage and swelling, known as edema. The damming or backward pressure theory explains this. When forward flow is blocked, blood pools, raising pressure in the veins and capillaries behind the obstruction. This overwhelms the osmotic pressure that normally pulls fluid back into vessels, leading to fluid leaking into tissues. In severe cases, like right heart failure, this can cause systemic congestion with swelling in legs or lungs. Want to explore how this relates to specific conditions or treatments?